So we're going to continue and set up some more volume problems. So the directions, once again, we're going to start off by generating a solid figure, revolving the trapped area around the given axis of revolution, and then we are going to set up an integral that represents the volume of that figure. So this next one, number 2, same curves as we had a moment ago. So I'm going to make the picture a little quick. We've got our x squared plus 1. One thing to notice about the pictures, everybody, you don't need to go so crazy for scale. So you may have noticed that I started to make this up and then I arched this out a little bit because x equals 3, I want to give a little bit of space, but I know that they need to hit. So again, most of our picture, it's not that they need to be perfect, it's just to have a sense of what's on top, what's on bottom, what's on left, what's on right. That's the kind of stuff we need. So that I know x equals 3 is somewhere over here and it'll hit this curve. That gives me my right edge. The x equals 0, that's the y-axis. Y equals 0, that's the x. So again, same shaded region that we had up here a moment ago, same startup. But now I'm taking that around x equals -1, okay? So x equals -1 will be over here, and we're going to go around that line. So now this is kind of similar, because again, the technique doesn't matter yet. Doesn't matter which volume technique, first just generating the picture, just to realize that now we've got a gap, that this is all solid, so when this comes up out of the paper and flips around, this gap here would be mirrored over here, and then we'd have our shaded region will be over here. So again, this space here is mirrored right here, and now we get our roundness, and that is our shape. So, you can try and talk about similarities and differences to previous, but we said that in the other video as well. Take the exact same area, revolve it around a different axis of revolution, and there's no reason at all to think that there's any connection between the shapes. So this one is a little more squat and wide than this one was up here. It still has a lot of open space in the top. Biggest difference, this one, that open space, that is there the whole time. I could literally put my pen from the bottom well, I guess it's a little too wide. So maybe something a little bit thinner. So just like this pen cap, this could literally squeeze all the way through from the bottom because all of this is open. But as we wrap around, your tire type shape, open in the middle, but you've got all this filled in as it wraps around. So again, as I do this, I'm really just going to be focusing on the peel technique, on making little slices and peeling off these rectangular slabs like I was doing in the previous. You can certainly come back and think about using the chop technique, but let's again focus on peel. This axis of revolution, I would chop by going across it, and I will peel by going in the same direction as the axis. And those 3 peel marks here, these are not 3 new peel marks on the left, that's the result. Make this slice, peel it off, and that this edge that came off here corresponds with this edge that came off over here. So there's our setup. We are again getting rectangular slabs. I still have my height and my base, and it's always 2 pi r for the base, h for the height. But before I go too crazy there, what is my thickness? Delta x or delta y? Again, these vertical marks is making this the thickness, this the thickness, this the thickness. So that makes delta x my thickness. My height, well, here's some similarity, but again, we shouldn't count on it. We shouldn't need to look at number 1 in order to do number 2. We should be able to look and make our own decision. And the height here corresponds here to here, here to here, here to here. And that is going from the x-axis to the y value on the curve in terms of x. Well, the y in terms of x is again x squared plus 1. So again, that worked out similarly to this one, but that's kind of a coincidence. You have to look at the picture and see that for yourself. But now R. Let's take what we realized in the last one. So let's focus on one R value. So in the last one, we were looking at this as one of our R values. This was the center, and that was the edge of my second peel, so that ended up being one of those R's. But that is not R here. This is R. This is my center, and that's what makes it a little bit messier. I'm not going from the y-axis over to here, I'm going from x equals -1 over to here. But we can still use so many of those principles about distance. From what we saw in the example above, this is x. From the y-axis over to here is x. Well, what about from here to here? Well, this is the y-axis. This is x equals -1. I know it's a -1, but think of the distance. This is a distance of 1 unit. So if this is 1 unit and this is x units, what is this? X plus 1, or 1 plus x, either way. And that is the R value in this problem. Now don't get too frustrated. I said this as soon as we did the first one. R is the frustrating point, but that's the idea to get R. Think about what is just the basic x variable, or y, if necessary, and then think about, is that the actual R, or is there some adjustment to actually getting R? Here, that was the x distance, but that was shorter than R. How much shorter? It was always 1 unit shorter, so we added that 1 unit to the x to get our whole R. Now I'll set up my integral, 2 pi r times h times the thickness. How about my bounds? Well, my bounds are still x's, but what do I actually have to peel? Now here, this is where we don't peel something that's just completely open. Up here, we could talk about where there was space here, but it was solid down here. But this in here, this is just completely empty, open space. So where do we peel? Well, I start peeling on this outer edge, and this comes off, then peel here, and this comes off. And by the time I peel to here, this is gone as well. So I'm peeling from here to here. That was the line x equals 3. That was the y-axis, or x equals 0. So this will also have bounds 0 to 3. Now, that's the setup. In this part of the video, all I'm going to do is just a setup and stop. That's what I asked you to do. But just to realize, to solve, not that different from what I did up over here a moment ago. Here you had x times x squared plus 1. I multiplied it, then I took the anti while kicking the 2 pi out in front. Same thing happens here. 2 pi out in front. Here you just have to FOIL. It's not just x times x squared plus 1. You got to FOIL. This will not give like terms, but sometimes you would get like terms. Then you could take your antiderivative. Then you could deal with your bounds. One other quick thing to notice. Again, you don't get to pick your bounds. Your bounds are what they are. But notice, having a bound of 0 is pretty nice. Notice back here, right? You plug in 0 in this type of function and you just get 0. So just thinking about what integrals are easier to solve than others, well, all of them have little bits of cleanup. But sometimes cleanup is a little harder than others. This one certainly was a quick distribution. Here you'd have a little bit more to distribute and FOIL out. But then both of them are at least nice because they both have 0 as a bound. Okay, so let's move along. More examples, that's what's going to help us here. And for problem number 3, I'm still sticking with the same curves, but I'm again changing our axis of revolution. So one more time, my x squared plus 1, x equals 3, x equals 0, y equals, x equals 0, y equals 0. So that same trapped region. But now revolving around the line x equals 3. Well, where is the line x equals 3? Hey, it was already a part of my figure, right? X equals 3 was already given, so it's not a matter of where is it. By the way, remember, I can't have you revolve that around a line like x equals 2. We don't have any of that symmetry. That would not work out. But I could have you revolve it around something like x equals 5. That would be very similar to the previous. You would just have a big gap before you even start revolving. So think of that in the reflection. But here, x equals 3. Here it is. We're revolving around like this. And this up out of the paper flips over and across that axis. And we would have this type of figure. I think this kind of looks a little bit like maybe like a circus tent or a carnival tent, right? It's got the big poke in the middle. It's got its big pole, so it's highest in the middle. You have the flaps where you could enter. But again, it's a round, it's a, a big round tent. Okay, so there's my figure. I suppose you can also, there's plenty of other figures you could try and think about as well. This still not quite like a bullet because it's a little bit sharper and pokier here. Bullets tend to be a little bit more rounded on top for aerodynamic purposes, but either way, you could still kind of think of it like a bullet, just a little bit more of a pointy bullet. Okay, we're gonna peel. Now, the last two videos, it was like I was peeling on the right side, which led to peeling on the left. It's not about left and right. It's just like chopping. It's about using the original picture. This came after we revolved this, so let's focus on this piece. So if I'm gonna peel, I would make my first peel mark here, slice that, peel, and this would come off on this side. My second, this would come off on this side. My third, this would come off on this side. I still have all my vertical marks, but first things first, I'm getting my nice rectangular peel. My vertical marks lead me to a thickness of delta x. And my base is always 2 pi r, also going to need my height. The height, for the third time, a very different figure, but the height here to here corresponds here to here, here to here, here to here. X-axis to the curve y equals x squared plus 1, specifically the y value on the curve in terms of x gives us x squared plus 1. And now r, let's still use the same thinking, everybody. This is x, but that is not r in this problem. R is from the center to the edge. Here is the center. This is r, center to this edge. So I can go first peel, r is here to here, then here to here, then here to here, then here to here. But I'm already jumping, focusing on this one. Here to here is one value of r. I already know this distance is x. This is what I want. Well, what else do I know? I know that this is x equals 0 and this is x equals 3. So this gives me a total distance of 3 units, and r is smaller than that. How much smaller? Well, it's always x units smaller. So in my first one, x is 0, 3 minus 0 gives me 3. But then 3 minus this little bit gives me my second r. Then 3 minus this slightly bigger bit gives me this r. Then 3 minus this bigger bit gives me this r. So r is 3 minus x. Still a little frustrating, everybody. Still not easy, still not obvious, but it definitely takes a little practice. But if delta x is your thickness, r is gonna include the x to some capacity. Whether like number 1, r is just x and that's that, or number 2, you had to add something to x, or here you subtracted x from something. Those are kind of your possibilities. We put it all together, definite integral, 2 pi r times h times the thickness, and of course my bounds. And just jumping back to number 2 for a quick moment, my bounds were still 0 to 3. Kind of makes sense, like we started on the right and went to the left, but we still put them in order 0 to 3, thinking left to right. And now in this one, that's exactly what happens. We're starting right here at 0 and we're finishing right here at 3. So one more time, the bounds are 0 to 3. And this one, there's your setup. It's all I asked for. That is good. That's a good final answer. If you're going to solve it, this is almost identical to number 2. Kick the 2 pi out in front. Once again, you've got a little foiling work that needs to be done. And then you'd have to do your anti before plugging in your bounds. Okay, one more with the same basic set of curves, and then I definitely want us to look at a couple that don't have those same set of curves. But one more with those same set of curves, and just a few more problems to get some more good practice. So, number 4, let's get that same setup one more time. X squared plus 1, x equals 3, y equals 0, x equals 0. There's my trap figure. If I revolve this around the x-axis, very nice. Nice clean flip. Flip down here. We get this almost like a big bell, perhaps, that's kind of on its side, something like that. Very big, solid figure. Now, looking at this one, I have to mention, again, you get your choice. So I will show you how to peel this one, but this is one where almost all students universally prefer to chop. This is almost the perfect chop problem. It's all perfectly set up for chop. Chop across the axis of revolution. Your R is the curve, no adjustments. Your bounds are 0 and 3. Integral 0 to 3, pi, this squared, dx, that is the setup. So, wanted to point that out, but again, we should get a little practice with the peel, and this is why maybe you're already starting to realize the ones that peel that we tended to focus on are ones where we kind of have some sort of a vertical line as our axis of revolution. And then those vertical lines need vertical lines to be our slice marks and leads to delta x to be our thickness. Here, we'd have to use horizontal lines to go in that same direction. And now I still get a rectangular peel, but just to realize, now in that sense, this would be the height of your peel. This would represent the base, so this would be the 2 pi r, and now we'd have delta y for our thickness. But look at all this little messiness. I mean, this is just kind of a good bit ugly. I'm going to jump to the r value. The r, when we're going around the y-axis, r is x. Well, when you go around the x-axis, r is y. Your r from here to here, from here to here, from here to here. It's the y coordinate, and we want it in terms of y, no extra adjustments, so r is just y. But look at this mess for the height. The height is from here to here, here to here. So look at this. This is actually kind of similar to what we're seeing up here a little bit. I have to look at this whole distance is 3. This distance is the x unit on the curve, but I can't leave it in terms of x. I need to resolve it for y. Everything in this problem needs to be in terms of y, so we can't just look at this and say, oh, that's 3 minus x. Really similar. Look at that. Look at what I'm calling h here. Sorry. What I'm calling h here in this picture, that's pretty much the exact same thing we were doing as r in this picture. So again, you have to be able to draw the picture. Little mistakes going around the wrong axis of revolution, those are definitely going to lead to big problems, unsolvable problems, to be quite honest and frank. So we have to be careful with that. But now look at all this extra work. So I have to solve this for x in terms of y. Subtract 1, take the square root. We'll get x is equal to, y minus 1, and then I'll take the square root. Technically, I get plus or minus, but that's, this is the positive part, this is the negative. So I would have 3 minus that quantity. And we're seeing it's almost like the double whammy, so to speak. I'm shifting this in terms of y, which is not as easy, and I have to deal with this extra little weirdness. So there's kind of a couple little pain in the butt aspects, but we're almost done though. We've got 2 pi r times the thickness, times the height, times dy for the thickness. Bounds, we're peeling, so just peeling from here to here. By the time I peel to here, this entire bottom region will have peeled off as well. So what is up here? Well, again, I need y's. What's so special about this y? It's where this curve and this curve are intersecting. So what is the y value where that happens? Well, I just plug that in, and I would get that this corresponds to y equals 10. And that'll be my top bound. And my bottom bound is here. Well, that one's easy at least. That one is y0. But now look, setup, you're done. Definitely the hardest problem we've seen so far in this video. Not the easiest. And notice, when you take a slightly harder approach, this one again, you know, some problems are just simply people's preference, but one like this, you know, that disc approach works so perfectly, a little bit of foil, and you have a nice integral ready to solve. Not just easy to set up, but not that bad to solve. You want to solve this one, 2 pi kicks out, distribute the y, but you can't just distribute y here. That would have to be solved as a separate integral. 3y, you could solve that integral, minus this integral, y squared of y minus 1. That's where we would need a u sub. Not a big u sub, nothing terrible, but it would need a little bit of a u sub to clean up that little bit of a messy situation. Okay, but again, setup, definitely wanted you to see one where y was the variable, was the thickness in a peel setup, but most of the time, if that's happening, again, it's good to get the practice in the 5.3 homework, but then to think ahead a little bit, we're probably going to be more inclined to actually chop a problem like this. Okay, last couple. Square root of x, x equals 0, y equals 2. We're finally getting some fresh curves. So let's again take a nice, good little, take our time with it, get our picture set up nicely. So, same idea here. Oh, I'm sorry, I want this to go around the y-axis, not x. Let's take this around the y-axis. The square root of x, I call it the hook out of the origin. X equals 0 is the y-axis. Y equals 2, horizontal line up here. Now again, what we were saying about making this to scale and everything, these are going to hit eventually. So you don't want to draw y equals 2 up here. You want to make sure that it actually hits in your figure. So there is our trap region. If you did this around the x-axis, that is very similar to one we just did. That is almost another perfect disc washer problem. Just number 4, that was a disc. If you do this around the x-axis, you'd have this empty space in the middle, so it would be a washer. But those are both almost perfect disc washer problems. But when we take this around the y-axis, we revolve around up here. This up and out, flips over. And this, it's not perfect, but it's almost like those little spinny tops that some kids play with that, you know, can kind of just spin and pivot right on this little sharp point. So that's one way to look at it, but there's other ways to think of it as well, but it does have that roundness. And this one, this is still not terrible to chop. If you chop it, you'd have to chop horizontally. You'd end up with those horizontal marks, so delta y would be your thickness. You would need a little conversion, but not bad at all. So again, not a bad one to consider to use by chop, but let's peel. Peeling Same direction as my axis, peel, 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 which leads to these three sides also peeling. These pieces, I should say, peeling off. Back to our more traditional, so to speak, peel with the base in this direction. Delta x for the height, 2 pi r for the base, h for the height. We're around the y-axis. There's nothing special about finding r or h next. I just definitely recommend good picture, think about your technique, get your thickness, and now it's just all kind of the same. We're going to have to find h, we're going to have to find r. I'm just choosing to get r first this time. And if you want to memorize a fact, I don't recommend it, but we are going around the y-axis. If we peel and we're going around the y-axis, r is just x. But again, hopefully that's starting to make more sense why that is the case. What is r? First peel, it's here to here. Second peel, here to here. Third peel, here to here. Every single time we're just going from the y-axis to an xy pair, and the x coordinate would represent that horizontal distance. So r is actually not bad at all in this problem. H is a little bit more of a pain. Can you see h in this problem? Well, h in this first peel is here to here, very thin and little. Then it's a little thicker, then a little thicker. It's tempting, and especially if you're going too quickly, people just say h is the square root of x. People are now starting to make assumptions and not look at the individual situation, and they just plug in whatever equations they think might help, but to literally look at what's happening. This distance is the y value on the curve. This distance is the square root of x, but this distance is what we want. So again, we've got to play a little bit of those games. So you never know where it's going to come up, okay? You have to look at each individual picture and make good, smart, informed decisions. So the square root of x is not h. The square root of x just represents this distance from the x-axis to the curve. So that doesn't give me h, but it can help. What else can help? Well, I know this distance is 2 because that top line was y equals 2. So how do I get this little distance? Take this big distance minus this piece. H is 2 minus the square root of x. So we get the integral 2 pi x, because x is r, times our 2 minus the square root of x, times dx for the thickness. How about bounds? Well, that is where I'm starting, and this is where I'm finished. So I'm finished at x is 0. Again, as we said before, 0 does come up a good amount of the time, just because the x and y axis, they are often, not always, but they're often used as some of our boundaries. But what about this over here? Well, we got to do a little work. It's not obvious. It's not given. I mean, some people are always looking for x equals equations. When we had one here earlier, we had 2 x equals equations, and those led to our bounds. But again, you got to be able to look at each individual picture and realize this time, well, again, this is the important spot, but what's so special about this spot, it's where this curve and this curve are intersecting. So I have to plug this in. So 2 goes in place of the y here. So if 2 equals the square root of x, I could solve for x, square both sides, and x is 4. And that is my upper bound, and that is my setup. Solving, you still have to distribute the x. This is a little bit uglier, right? You just got to make sure you use your exponents correctly. Treat this like it's x to the 1/2 power. What's x to the first times x to the 1/2? You add the exponents, you get x to the 3/2. So it's a fractional exponent. It's a little bit uglier, but still, sorry, that's a 4, just so that's not messy. That's just a 4. So fractional exponents certainly still can come up. So still good practice with solving, but still not bad. Basically just a little bit of a multiply to clean up, and then you're ready for your antiderivative and plugging in your bounds. Okay. Last one. Again, everybody, this is not an easy topic. You really need to get some experience, so the videos help, good examples in the book. At the very beginning of class, I gave you links to Dr. Bob's extra videos. Some people just like those as just a few extra examples that they could see work through. Same thing with Dr. Yee's book. He had fully worked out problems. So sometimes just to see a few more fully worked out problems, experience can really help a lot here. But then I also want you to remember, we're still going to see a lot more review as we mix all this together. So we're still going to get a lot more practice when we come back next week and get into our next video. But again, let me finish this up. So here, same initial curves. The hook, the straight line, oops, it's a little tight. And the y-axis. Now we're going around x equals 4. Now, because we have already done this, this was a nice little bonus. That makes it clear 4 is this point of intersection. But we know it can't be over here. That's again, you can't have your x value in the middle of this without having symmetry to revolve around and make a good clean shape. But there was an issue of, is it right here at the end where the curves intersect, or is it out here and is there some extra space? And if we had not already done this work, we would have to do it now. We'd have to realize we have to worry and wonder about this x coordinate, and we'd have to realize we would find that x coordinate by looking at the intersection of these two, but then we'd realize that is x equals 4, so we know, yep, that is perfect, that is where we are revolving our curve. Oops. Sorry for my little messy picture here, but now that's our shape. This is almost like, you can almost look at this as like an indoor area. Like this is all open space with we've got this roof over the top of our head, but it's still a little bit of a dome because we've got this round shape as we revolved around this axis. Or if you flip this around the other way, if this was my picture, this is almost like a big satellite dish, right? That it could echo and reflect all the different wavelengths. But either way, just to have a little something to visualize. And now we're going to peel one more time. So I'm going to start peeling on my original section over here, a few peel marks. The result of those peel marks is that these regions come off over here. This again gives me my nice rectangular piece that opens this way, delta x for my thickness, 2 pi r for the base, h for the height. Very different curves, shapes, and everything here, but the height here is the same thing as it was the height here. If you look in this picture, the height from here to here, from here to here, from here to here. I know we started on this outer edge, and here we're starting on this side, but it's still the same thing. I need this distance for my height. This distance is the square root of x. This whole distance is 2, so this in between is the big distance minus this piece. How about r? Well, now we're not going around the y-axis, so we can't just say it's x, but we can start to expect that x is going to be a part of it. So let's see where x is versus what is the r that we want. So r goes from here to here, here to here, here to here, here to here. But x, let's just pick one of them. So I'm going to focus on this one. That is one r value that we're looking for. But where is the distance x in this picture? X would be from here to here. So if I know this distance is x, how does that help me find this distance over here? It comes back to this last piece. We know that is a total distance of 4. So if this piece is x, then this piece is 4 minus x. We use different, here we're using the equation from the curve, here we're just using the generic x value, but these are similar principles. Neither one of these situations, h nor r, did we have a perfect situation? Both of them needed some little adjustment. And that adjustment came from what is it that we know and how can we use that to get what we want? Well, that's too big, so I have to subtract this piece. Same thing here. My r is smaller than that, so I have to subtract something from that. Oh, I subtract the x. Hey, the square root of x is not my height. This is my height, but that's too big. How much too big is it? Oh, it's the square root of x too big. That's what I will subtract off. So that's it. So I've got 2 pi r h times the thickness, and we're still peeling from here to here. So once again, 0 to 4 for bounds. Setup, that's it, that's perfect. I hope you realize as we've been doing this, there's lots of little cleanup that you can do, and that's necessary if you're going to solve. But when I say setup, I just need to see bounds and then any of the other variables, whether it was cap r, little r in the in the chop, whether it was discs or washers. Here, your r and h, those are the things that have to be worked out, and that is a full setup.